안녕하십니까. 로데슈바르즈 코리아의 최지홍입니다. 오랜만에 찾아뵙는 것 같습니다. 오늘 참석해 주신 모든 분들을 환영합니다. 오늘 저희가 준비한 웨비나는 와이파이 7에 관련된 내용입니다. 와이파이 7 아직 정식으로 출시된 건 아닙니다만은 많은 분들이 관심을 가져주시는 부분들 중에 하나입니다. 그래서 오늘 이 부분에 대해서 어떤 부분들이 우리가 생각해 볼 수 있는지, 어떤 일들이 벌어질 수 있는지, 이런 부분들을 좀 이야기를 나눠볼까, 여러분들 그 주제를 잡고 오늘 웨비나를 준비했습니다. 오늘 웨비나 진행을 위해서 저희 로데슈바르즈 코리아의 기술지원팀에서 근무하고 계시는 이웅비 매니저 자리 함께 해주셨습니다. 인사해 주시죠.
네, 안녕하십니까. 로데슈바르즈의 기술지원팀을 담당하고 있는 이웅비 매니저입니다. 안녕하십니까.
예, 오늘 와이파이 7에 대한 이야기를 한다고 했습니다. 오늘 어떤 내용들을 이야기하게 될까? 오늘 주제를 잠깐 말씀을 해주시죠.
금일 웹세미나는 와이파이의 기본적인 원리에 대한 부분을 설명드릴 예정이고요. 그리고 지금 화두가 되고 있는 와이파이 6와 와이파이 6E에 대한 내용을 설명드릴 예정입니다. 그리고 금일 웹세미나의 주제가 될 수 있는 와이파이 7에 대한 내용을 얘기 드릴 예정입니다.
지금 현재 상용화되어 있는 부분은 와이파이 6까지인
네,
게 맞죠?
맞습니다.
예. 그래서 오늘 그 최신 와이파이 트렌드에 대한 내용들을 가지고 말씀을 드리게 될 것 같은데요. 오늘 저희 준비된 동영상은 저희 본사에서 글로벌 웨비나로 진행했던 내용들을 저희가 자막 처리를 해서 여러분과 함께 나눌 내용으로 준비를 했습니다. 생각보다 길이가 조금 깁니다. 그래서 오늘 지체하지 않고 바로 지금부터 준비한 내용대로 시작하도록 하겠습니다. 지금부터 동영상 내용으로 함께 내용을 보시겠습니다.
Hello, welcome to today's webinar about one of the hottest topics in the wireless industry, Wi-Fi 7. My name is Jörg Köpp. I'm Market Segment Manager at Rohde & Schwarz, and it's a pleasure for me to welcome to this webinar also Werner Dürport.
So, hello everybody. My name is Werner Dürport. I'm Product Manager for non-cellular measurement applications, for ultra-wideband, Bluetooth, and for our today's topic, Wi-Fi 7. So, besides the slides, I would like to show you today something in practice on measurement devices. But at first, we have to start with the theory and key facts of Wi-Fi 7.
Thank you very much, Werner. Yeah, that's a good point. Let's start to look a little bit on Wi-Fi, where we are today in the industry, and give a little bit motivation why we have this webinar and why is everyone talking about Wi-Fi 7. If you look on the latest market forecasts and statistics, and it's basically from the Wi-Fi Alliance, then we see already 18 billion devices on the market. Just to put this in the perspective, we have around 8 billion mobile devices or mobile subscription based on the Ericsson report. So you see quite a lot. And of course, majority of mobile devices have also Wi-Fi on board, not to forget this. If you're looking on shipping just in this year, 2022, they're expecting 4.4 billion devices. So a lot of investments also in Wi-Fi. And if you look on the latest Wi-Fi technology, the actual Wi-Fi technology, Wi-Fi 6, there's already 50% adaptation. So that means new devices are all more or less all supporting Wi-Fi 6. If you look on this market forecast on the right-hand side, you see this, what I mentioned before, there's a lot of Wi-Fi 6 devices now on the market, and we talking today about Wi-Fi 7. You have probably seen in the last couple of months a lot of announcements from chipset vendors that they are already working on Wi-Fi 7. And if you look on the protocols or on the discussions on the Wi-Fi 7, on the Wi-Fi Alliance, Wi-Fi 7 and on IEEE, there's a lot of activities there, and the first plug fest are already planned, so that's a hot topic. But anyway, the first devices are expected for 2024, 2025 on the market. But as I said, the industry is working today on this, and therefore they are looking for test and measurement solutions, and this is exactly what we would like to talk today about. But start a little bit on the technology, and I think it's worthwhile to look first of all on Wi-Fi 6, because that's really the base for Wi-Fi 7 and everything what is introduced there, and it's very important. What was the main motivation of Wi-Fi 7? It was about high efficiency, especially due to the big success of Wi-Fi and also using Wi-Fi even in big venues or on airports and so on. There were so many people which would like to have access to Wi-Fi networks that there were some problems with the efficiency that needs to be solved. What is the essential problem of Wi-Fi 7, of the traditional Wi-Fi, is the principle of Wi-Fi that all devices are more or less independently, and they are looking on the medium, whether the medium is actually free to get access to the medium. So there's no central control or something like this. It's just looking on the medium and look what happens. You see this here on this graph. For example, this should indicate the medium, and here you have, for example, 3 different stations that would like to have access to this medium. And the principle is that they first look on the medium. If this is free, then they can use the medium and start transmission. If it is not free, for example, here on the second phase, then they have to wait certain time, and there's some back-off timers and so on and so far. So this works quite well if you have just a limited of stations which would like to have access to this. Of course, it works best if you have just a single station. And this is what you see on this graph here. If you have this kind of very limited number of stations, then you can really fully use the medium and fully use the capabilities of the access point and the stations. But if you have more stations and users which would like to use this, then the overall throughput of this Wi-Fi networks goes dramatically down. So you can compare this with this traffic jams that you see here on this graphs. And this was the main motivation for Wi-Fi 6. What are the main technology or the cornerstones of Wi-Fi 6? They introduced essentially a kind of resource management. For this, they introduced OFDMA. That means they are able to separate the spectrum in the time and in the frequency domain. So formally, you have just a Wi-Fi channel, and you have a certain time where you can use the Wi-Fi channel. Now this is also splitted over time. So that means during a certain time, also different stations can use this at the same time. So you have a more fine granularity of the access to the spectrum. For this, to manage this, they introduced resource units. And these are the main points to have this kind of controlled network, which is essentially a kind of trigger-based communication. In addition to this, as I mentioned, there was also the need to cover more these big venues, other multipath environments. And for this, they introduced the longer guard interval to get rid or to better deal with the intersymbol interference stuff and so on and so far. But if you introduce a longer guard interval, you immediately lose efficiency, because during the guard interval, you cannot transmit any data. To make this more efficient again, they changed the subcarrier spacing, and for this have a longer symbol time, so that the relation between guard interval and the use symbol time becomes more efficient or more appropriate. And these are the main changes in Wi-Fi 6. If you are just looking on the table, what are the main differences on the physical layer? I'm just focusing here on the physical layer. What they introduced in Wi-Fi 6 was this OFDMA, this new subcarrier spacing, what I mentioned, new guard interval, so some options to deal with the actual environment, and this was all about efficiency. They introduced also a higher modulation scheme with 1024 QAM, which were also adding a little bit more speed on the single link, but not so much. So in fact, if you also look on the numbers here, which are very theoretical numbers, there's not much improvement in the speed, but there's a lot of improvement of the efficiency and the overall throughput of an access point. So this was Wi-Fi 6. If you look on Wi-Fi 6 and the available spectrum, which was at this time basically 2.4 gigahertz spectrum, which is very small, and the 5 gigahertz spectrum, and have in mind they defined already 160 megahertz channels, it was very hard to find any area where you really can use this. In fact, you have just 260 megahertz channels in the 5 gigahertz range. So that means the capability of Wi-Fi 6 or 802.11x AX, you not really use. And especially with the latest trends, you know all this with the pandemic, more homeschooling, more home networks, homework, and so on. There was a strong demand to have more Wi-Fi capabilities. And the regulatory organizations were looking on this and were addressing this, of course, also pushed by the industry, and were now making available the 6 gigahertz bands. And you see this here. This is a lot of spectrum compared to this what we had before, especially if you look on the North American market based on FCC, where you have really 1.2 gigahertz spectrum available for Wi-Fi and of course also other technology in the unlicensed area. In Europe, it looks a little bit different. Let's have a short look on this, how this looks in detail, because as always, there are very specific regulatory requirements for the use of the spectrum, and it's worthwhile to have a look on this to understand what are the implications probably for your solutions. If you look on this map, and this map you can update more or less every day, because new countries are coming on this map, getting from light blue to dark blue. Dark blue means here the regulation is already there, it's approved, and you can use Wi-Fi 6 or the 6 gigahertz band. The light blue means that there is a country where they are actually considering this, have the discussions, what is possible, what are the rules, and so on and so far. And you see there's a couple of countries already on Wi-Fi 6, especially the North American and also the European market, Latin America a lot, and there are also more and more Asian countries coming up and using this. So that means 6 gigahertz is now available. Looking a little bit on the details, I was taking here 2 examples. One is Canada for the North American market to explain a little bit the principle. The other is Germany for us, one representative for Europe. They essentially distinguished in all these areas 3 different applications, if you like. One is standard power, what you see here. The other is low power indoor and very low power. Standard power means you can really use the standard 36 dBm power, but only in certain regions over a certain bandwidth. Here, for example, for Canada, you see you cannot use this over the whole 1.2 gigahertz, just part of this, the larger part of this. And there are certain rules how you can use this. For example, you cannot use this in cars or on trains. And you have to use an automatic frequency coordination function, which means you have first of all to ask a database whether you are allowed to use a certain channel in this area and with which power. So that's really a kind of spectrum management which is required for this. This is how it is defined in Canada actually. Then there's low power indoor. Low power indoor means it is only allowed to use this indoor. This also means, for example, an access point needs to be powered by a power cord. It is not allowed that this access point is powered by a battery, for example. And you have certain requirements here. Of course, with lower PSD and ERP, so just 30 dBm. And then in some countries, we have something for very low power. This is just for mobile devices. That means for device-to-device communication with very low power. Probably very interesting for some applications like virtual reality, where you communicate from a smartphone to your glasses or something like this, with very limited power as well. So this is Canada, for example. If you look now on Germany, it's a little bit different. The standard power is not applicable for Europe at all, and as I know, also not in discussion. It is just low power indoor and very low power. What you have to have in mind, the spectrum which is available in Europe is much smaller. It's just around 500 megahertz, just the left-hand part of the 6 gigahertz band. And they have a little bit different ERP values. For example, for low power indoor, this 23 dBm, and here for this very low power, they have this 40 dBm. So, and you have really to look on every country what is defined there. As I said, there are also some specific rules about use in cars, in airplanes, and so on and so far. So if you are in this industry, you should have a look on this. So this is Wi-Fi 6 and Wi-Fi 6E, but we would like to talk today about Wi-Fi 7. And Wi-Fi 7 is now about high throughput, and in fact about extreme high throughput. That's the name about. But before I would like to go to the details how they reach this very high throughput, I would like to make a little bit housekeeping, because there are some changes in general which are a little bit about backward compatibility and looking in the future, but worthwhile to know this stuff as well. So first of all, they introduced a new preamble design, which should be future-proof. You see this here, this light blue one. I would not like to go in the details. Werner will show you a little bit about this later in the demo. The main idea is that you have here now really, you can put in here the different versions. You have some parameters, for example, which bandwidth you are using, BSS color, and so on and so far. You can have a look on the details, but this is completely introduced new. Of course, you have still the legacy preamble to have backward compatibility and so on and so far. The second thing what you should be aware about is that they make a new tone plan. They modified this a little bit. What was the reason? The reason was, especially if you are looking on the 20 megahertz borders of the spectrum, which is especially important for preamble puncturing and also some regulatory issues, you would like to split the spectrum in 20 megahertz slices, if you like. And with the actual tone plan, with 80 megahertz, for example, you had some problems with some tones. It was not perfectly fitting. Therefore, they introduced a new tone plan where this fits now very well. Just that you are aware of, there's a new tone plan for 802.11be Wi-Fi 7. The next thing is, and this goes already in the direction of more speed and more throughput, because one of the measurements that you can do on the physical layer just provide more resources, more capacity, more data channels, if you like. And they introduced now the 320 megahertz channels. And these 300 megahertz channels are only available in the 6 gigahertz band. So you see the 6 gigahertz band is also very important for Wi-Fi 7. And even if you have 1.2 gigahertz available, 320 megahertz, you can have just 3 channels placed there. Therefore, they allowed now for more flexibility overlapping channels. So they defined in the sum 6 320 megahertz channels. So if you are North America, for example, Canada or US, and you have probably this 1.2 gigahertz available, then you have up to 6 300 megahertz channels that you can assign. If you look on Europe, you see this here, you have in fact just 2 320 megahertz channels. So good news, you have this broad channels, you can make extreme high throughput with this, but of course it's not everywhere available. And we will come later to a point about preamble puncturing. In fact, now where you see how you can use this more spectrum also more efficient. Coming exactly to this point now. Preamble puncturing. So if you, for example, would like to use as access point or as network and 320 megahertz channels, this is indicated here. You would like to do this, use this channel over the whole bandwidth. You have here a primary channel and here all the secondaries. But of course, you are not alone. Typically, there are other networks around you that are also using some spectrum or would like to use this. For example, in this example here, at 40 megahertz access point, here and under with 80 megahertz. So if this happens, then you make this looking on the medium and you recognize, okay, I cannot use the 300 megahertz channels because some other users are actually using a small bandwidth of this. So that means normally if you have no preamble puncturing, you will have to fall back more or less to 80 megahertz. So you cannot use the 320 megahertz, that's not possible because of the others, but you also lose all the other free spectrum, it is also not available. And therefore they introduced this preamble puncturing, and what you can do with this, you can now really use all the still available spectrum, like you see here, you have here this 80 megahertz and you combine this with 120 megahertz here. Of course, you cannot use the full 300 megahertz, but you can at least use what is available. And this is, of course, very important for an efficient use of the spectrum and to reach the throughput that you would like to have. Of course, not all combinations are possible. Here in this table shows you just the possible separation for preamble puncturing for 300 megahertz PDDU. You have to look on the spec for all the details. Finally, another thing what they introduced for more efficient use is multiple source units per user. In Wi-Fi 6, they introduced the resource unit. So one resource unit for one user. If you take here the example, for example, you have here resource unit for 26 tones or 52 tones. And here, for example, for 106 tones. If you take one example, for example, you have 8 users, you would like to assign each of these users 106 tones resource unit, then you get in the situation that you're not using the whole spectrum because you have always a gap here, if you look on this slide. With multiple resource units, where you can now combine a 106 resource unit with a 26 resource unit, you can at least some users give more spectrum or more tones. And this, of course, improves the efficiency because then you are really using all tones which are available and can distribute it over the user. So that's for efficiency. For the small resource unit, this is designed like this. You have to have in mind these are always resource units which are continuous. That means close together. For the bigger resource unit, and this is essentially also important for this preamble puncturing, so if you are not able to use the full channel, you have also the possibility to combine a non-continuous resource unit, like you see here, for these tones. So these are the two new things, multi-resource unit. We will see this later in a kind of demo as well. If you look now on tester measurement, then there are, of course, the typical measurements of the physical layer that you know from more or less any Wi-Fi standard that we had before. So the spectral flag noise, center frequency leakage, some about sensitivity, RX, channel rejection, minimum input level. You have, of course, a spectrum density. So that means you have a spectrum mask. You have a new one, of course, for 220 megahertz, but the principle is still the same. You have still puncturing mask. Of course, you have now more because you have more channels, you have more possibilities. So this will probably extend your testing effort to look on all the different combinations. So it would be good to make this easy. And for the multiple resource unit, in general for resource unit, we had the measurement of the so-called unused tone error. Now you have to adapt this for multiple resource unit. If it is continuous, like you see here, then it's quite simple. It's a very similar principle that you have for single resource unit. Just handling this as a bigger resource unit. But for non-continuous, like you see here, you have also some measurements between the used resource unit. Then, of course, you have a new transmitter cancellation area with a higher modulation scheme. We will come to this later. And you have all this test and measurement stuff, which is really related to the trigger-based communication, which is about power accuracy, trigger-based communication, RSSI measurements, and so on and so forth. Yeah, and with this, I would like to hand over to Werner to have now a look on real Wi-Fi 7 signals on our instruments.
Okay, thank you, Jörg. Thank you for explaining the history and also the first key facts of Wi-Fi 7. So, at the beginning I have mentioned, so I would like to present something in real, how Wi-Fi signals look like, how the signals can be generated and analyzed. For that, I have two devices with me. On the left side, you will see our signal generator SMW200A, and on the right side, the FSW, our signal and spectrum analyzer for the analysis of Wi-Fi 7 signals. Some details about both devices. The SMW200A is a vector signal generator which works for frequencies up to 67 gigahertz. He can be equipped for the generation of signals with a bandwidth of up to 2 gigahertz. And the generator has an outstanding phase noise performance, which is of course necessary to achieve very good Evm performance numbers. Besides the normal signal generation, we can also equip the signal generator with some additional options. One option is for fading. So in this case, one can simulate some reception cases well defined. And also the generator can be equipped with a second RF part for some MIMO measurements. For the FSW, we have different models which works up to 90 gigahertz in frequency. It's amazing. We have also bandwidth options up to 8.3 gigahertz for the analysis bandwidth. And of course, signal analyzer must be as good as the signal generator at least. So also here we have an excellent phase noise characteristic and also a very high dynamic range. This is essential also to achieve very good EVM performance numbers. So far about the theory and the measurement devices. Let us start now with a short demonstration to providing you a first impression about the characteristic of Wi-Fi 7 signals. For the demonstration, let us start with the generation of a Wi-Fi 7 signal. Here we can see the user interface of the signal generator SMW200A, which is able to generate signals on 2 signal passes, but here for the demonstration we are using the signal pass A. The block diagram shows the different stages of the signal generator. Here the stage of baseband signal generation, and on the right side the IQ modulator and the RF part to generating the signal. To generate a Wi-Fi 7 signal is very simple. So we have to go to the baseband part. We have to select the Wi-Fi standard. By the way, the generator of course is able to generate a wide range of different standards which partly also compete against the frequencies in the Wi-Fi band. Sometimes it's very useful to see also how the different signals can scope within the same frequency range. Wi-Fi 7, you have heard it, the new one is bandwidth, channel bandwidth up to 300 megahertz. So for that I have selected 320 megahertz already. And step by step now we have to describe the further characteristic of the Wi-Fi 7 signal, including data content which is necessary for performing the measurements. For that you have to go to the frame blocks and to build step by step the characteristic of the signal. At the beginning you can select the 11BE standard, the new one. Here you can see the option gives also the possibility to generate the former standards. As data type we have selected the data physical mode, and here the TX mode is already set to extremely high data throughput mode with 320 megahertz. And furthermore, we have now to configure the data content and the further parameters. For that, I go to the measurement screen or setup screen for the PPTUs itself. Here we have selected a very simple setup with just one stream, one single user, and step by step here you can now change the different signal parameters. With Wi-Fi 7 also some packet extensions can be defined. Then regarding signaling, we have now a new universal signal field, which gives information about the signal. Is it a downlink signal? Is it an uplink signal? You can select the OFDM-A mode. And also here some further parameters can be set. For example, here's the PBS color mode, the modulation scheme of the signaling. And here you can also differ between the 2 different PPTU units which are defined with Wi-Fi 7 between multi-user and triggered mode. Furthermore, here you can set up the guard interval. We have heard it based on the smaller carrier distance. We have now longer symbol times, which provides also an additional advantage regarding robustness. So a longer guard interval is able to dealing with more echoes, and also longer symbol duration gives the possibility to have also a little bit more time for the channel estimation. In the next step, we have to configure the user setting. Here in this example, we have just one user, and we have chosen here a resource size of 4 times 996 tones, which means at the end we will have here the 300 megahertz, 20 megahertz bandwidth. For the content of the PPTU, I go to the data section. Here you will be able to define the modulation scheme. So with Wi-Fi 7 we have 2 new modulation schemes 12 and 13, which differs only in the code rate, but both means 4,960 QAM modulation. To the data, or here before. For the data, we have here internally the possibility to generate randomized symbols and data symbols, which provides us the content for the measurements. And on the data side now, you have here an overview about the signal, how the signal look like after the generation here, with the different parts of the signal preamble, and here's the data part with a certain number of data symbols. So that's all on the generator side. The only thing what we have to do is now to switch it on and to activate the signal here. This brings me to the spectrum analyzer. Here, now the spectrum was with a whole frequency bandwidth. So here the FSW is able to measure signals up to 26.5 gigahertz in this model. Then here in view to the spectrum a little bit more in detail. So I have chosen for the trace mode a max hold functionality, which gives a better impression or also presentation of the spectrum. Here we can see now the 320 megahertz wide spectrum of the signal, and divided here in 80 megahertz parts, which means we have here unused tones in the middle. And here also between the 80 megahertz wide part here, we have also additional unused tones here in range of 40 megahertz. That means unused tones are necessary to protect the signal parts to each other if other signals are used also with dedicated bandwidths. That's a view on the spectrum analysis, spectrum side, but let us have now a view on the signal analysis. For that, I will start the analysis functionality. So with the mode button, you have the possibility to start the Wi-Fi analysis application. So for that, I have to make a trigger to the signal parts. And here on top, you can already see the captured IQ data from the Wi-Fi 7 signal, which is sent out or generated in packages. But at the end, we have, or at least we have to define a little bit more for a real demodulation. So here by the signal description, we have to say also the FSW, which kind of Wi-Fi signal do we like to analyze. It's here 11BE. So everything will be done automatically by an auto detection functionality, which takes care on the set signal parameter. Here on the lower left corner, you can see already the constellation. I can also zoom in a little bit. Here you can see the 4096 QAM modulation, which is amazing. And as Jörg already mentioned, here it's also a challenge sometimes to make the measurements or to have an error bit-free signal based on the very low distances between the different symbols. What can we say in addition to the signal? Here on the lower part, you will see the Evm measurements and some other parameters, which gives the first impression about the signal quality on the physical layer. But to explain you a little bit about the new signal fields, so we have to open a new measurement screen. So by selecting some, here's the signal fields. So I can move in this measurement screen here. And if I zoom in by the signal fields, you will get an overview about the new details about the ETH preamble. We have still a legacy part, so which is important to consider also the previous variants of the Wi-Fi signals here. But more of interest is now here's a new part, or the new parts for Wi-Fi 7. Here we have now the EHT universal signal part, which gives the information about the standard itself. So it was mentioned that in the preamble it differs to the previous Wi-Fi versions, that here now is a clear indication about the version and which is used here for the Wi-Fi, and here in this case ETH. Then another bits signals the bandwidth of the signal, here in this case 320 megahertz, and as seen on the generator side already, you will find the information which is set on the regarding BSS color and some other details here. It's done for the different packages of the 300 megahertz signal. Here first information regarding puncturing. This will be a part of the next measurement here. And you can see also how, for example, the signaling bits are modulated and so on. And as I said, it will be repeated for the other parts of the 300 megahertz signal. So in this case, it's very simple to analyze Wi-Fi 7 signal regarding the most important parameters on the physical layer, but also in addition regarding signaling of such a Wi-Fi 7 signal. To show you another feature, the puncturing, so I have to go back to the signal generator, and I have now to load a new setup which enables a fast switching to the puncturing setup. So it's done. And let us have now a look what I did. On the signal generator side now, I go back to the signal. And here I have now go to the user setting, which was found here. User configuration. Now you can see what does it mean, puncturing. So here we have the setup defined for one user, but you heard it. It's possible to combine meanwhile resource or parts of the resource units in a combination, so that we have some gaps, which gives also some other transmissions the possibility to get in and to have more transmissions in parallel compared to the other standards which allowed it just only an assignment of just one package or resource unit package to one transmission. Here the graphs shows now the configuration, and here the puncturing is defined in tables where user or the access point and the devices can decide which part should be used or where should be the gap. Here, for example, I switch now from 2 to 4, and you can see it here now. We have here MRU index 4 set, and you can see it here now a gap on the 4th position. So up to 7 positions, it's from 1 to 7. It can be defined, and MR unit index 0 means so we don't use any puncturing. Let us have a look now to the Spectralizer and Signal Analyzer side, how such a punctured signal looks like. Let me start here with the spectrum. Now you can see a gap on the 4th position defined by the index. Here we have now defined a gap of 40 megahertz within the 320 megahertz wide signal. On the signaling analyzer part, here again, the table of the signaling of the preamble. And here you can see now here's information regarding puncturing. So where is it? Here it's set up to force. That means by the preamble signaling, so the signal analyzer will follow the changes and will continue with the measurements here. Important is also to take care on the spectrum itself so that some criteria are fulfilled. So in the Wi-Fi 7 standard, some spectrum emission masks are defined. So also for punctured signals, which will be shown here. Here you can see now the whole spectrum with a gap on the 4th position. And here also we have here defined or predefined spectrum emission masks to check the criteria if everything is fulfilled regarding the outband spectrum and within the punctured frequency spectrum. So to take care that the Wi-Fi signals will not to impact or to each other. With the first part of the practical demonstration, so was my intention to provide you a first impression about Wi-Fi 7 signals. But we have much more to telling about in theory and later on also again in practice. For that, I will hand over to Jörg again for some additional facts about Wi-Fi 7 signals.
Yeah, thank you very much, Werner. Cool stuff. But now we have the real cool stuff on Wi-Fi 7 because we would like to talk now about extreme high throughput. So how you can achieve extreme high throughput with Wi-Fi 7. That's the topic for the next couple of minutes. I was taking here a very simple formula that you probably all know if you are working in the Wi-Fi industry and essentially applicable for every wireless communication interface. So what you can do if you would like to achieve extreme high throughput or you would like to improve the throughput on your channel. And this is more or less indicated by this formula. Of course, you can look about the spectrum or the number of data carriers that you have available. We talked about this already, that we are going now to 220 megahertz. Then you can look on the modulation, how many bits you can put in one single symbol. This is a number of modulated bit. This is about the, for example, here QAM modulation. This is just 64. It's probably not enough for extreme high throughput. So we have to talk now about much higher modulation schemes. Then the coding rate, this is more about the reliability, but has some impact on the data throughput, of course. The symbol time we talked about has some impact, of course. And then the other dimension that you can change is, of course, the number of spatial streams. So the MIMO schemes. In this example here, a 4x4 MIMO, you have, of course, always to have in mind, it is not always possible to add more and more antennas to the device. This is probably a possibility for an access point and for a notebook or for a PC. But if you look on the mobiles, which is probably the most common device using Wi-Fi, it is more or less impossible to integrate 8 or 16 antennas. But anyway, this is one possibility. And if you look now on a kind of real theoretical example, which sounds a little bit funny, but let's make a little bit calculations. And I was taking here a prominent example, which is very often used for Wi-Fi 7 as a motivation why we need this. It's argumented virtual reality and smart glasses. And I was taking here this nice lady with the smart glass. And you can integrate here, this is a common sense, up to 4 antennas. That means you have a MIMO scheme of 4x4. And you take the highest modulation scheme, what is available, and the highest bandwidth, which is available in a certain standard. And what I'm drawing here is a different maximum speed that you can achieve on the physical layer. And you see here for Wi-Fi 5, you can achieve, which is 802.11 AC, up to 3.8 or 4 gigabit per second. If you are going now with the next standard, this was Wi-Fi 6, and as I mentioned, there's not so much in improving the throughput because the MIMO scheme is the same, the bandwidth is the same. There are just a little bit about the modulation scheme. You can achieve 4.8 gigabit per second. And now with Wi-Fi 7, we introduced higher modulation schemes. With 4096 QAM, we have up to 16. In this calculation, this is still 4 because of this example. And we have the 300 megahertz channels. And what you can see here in this theoretical calculation, you can achieve up to 11.5 gigabit per second. That's really a lot. I mean, you can really think about how to bring so many data speed to an access point if you would like to bring this to these classes. But this is what is behind this on the physical layer. It is the number of antennas, it is the bandwidth that you have, and it is the modulation scheme. And these are exactly also the test and measurement challenges that we have to talk about, because you see this here. If you go from, for example, 11 AC from 256 QAM to 11 BE with 4096 QAM, you see here how close the constellation points are coming. And it really means you need a kind of perfect RF chain to achieve an EVM of minus 38 dBm. And this is a general challenge now in this new instruments or the new Wi-Fi standards. It is about Wi-Fi 6E, where you have now these 3 bands that you have to support. So more or less 3 different RF chains. You have this high MIMO schemes. You have this EVM requirements, 320 megahertz channels in a 6 gigaband hertz band over 1.2 gigahertz. And then this EVM requirements, because of this high modulation scheme, this is really a challenge in different aspects for the RF design. It needs to be measured, and it is one of the hot topics in the industry, how you handle this. Not to forget about power efficiency, terminal stuff, and also topics like in-device interference and so on and so far. And this is exactly the point where I would like again to hand over to Werner to look a little bit how you can measure this and how this looks like with this high-end RF, which of course also requires high-end tester measurement instruments.
So thank you, Jörg, again. Yeah, you have seen to achieve a minimum requirement of EVM, which is based on 300 megahertz bandwidth, very high. We have to consider by the tester measurement equipment some settings, of course. At least the performance of the measurement devices must be in a sufficient range, but also we have to consider different facts which have an impact on the EVM performance measurement. For that, I will demonstrate and show you some hints about the settings on the generator side and on the analyzer side. You have seen how easy a Wi-Fi signal can be generated and analyzed, but a second part of the measurements, of course, is performance. You have heard it before with the new modulation scheme of 4996 QAM. We will have new challenges, also coupled with a higher bandwidth of 320 megahertz. That means for powerful measurements, you have to take care on an optimal setup on the signal generator side and on the analyzer side. On the signal generator side, I went back to the block diagram. So I've told you we have here the baseband part, which describes the signal itself, but we have also here the IQ modulator and the RF stage, which amplifies the signal at the end. And for the best performance, you have to take care that everything is set up very well. And for that, you have to take care on the frequency response, for example, that the IQ modulator works without any offsets and so on. And it could be a little bit complicated to take care on every setup. But here on the generator side, we have implemented a nice feature which is named Optimize EVM, which takes the most of the optimization steps for you in an easier way. If you go to the analyzer side, just to show you the difference, here we have on the analyzer side, here's the summary display, which gives the overall EVM for the current signal. And we are in a region of roughly minus 47 dB. But if I go back to the signal generator and switch on the EVM optimization, you will see afterwards a certain improvement. For that, I have to start the measurement again. And now, before we were in the range from minus 47 dB EVM, and now we just by the tick on the switch on the generator side, now we have improved the measurement performance or the signal quality of the signal generator to minus 48.5 dB. So it's much easier now to take care on the generator side. On the signal analyzer side, we have also some possibilities to improve the EVM measurement performance. For that, we have here the soft key channel estimation, which provides us different kinds of settings. Let me start on top. We have here the channel estimation range, which can be differ between payload and preamble. So preamble means the channel estimation will be done just on the short part of the signal. And with the payload setting, we can do the channel estimation on the whole part or on the whole signal, which gives a better channel estimation and which results in higher EVM values, higher EVM performance. Then we have here also some other settings here regarding phase, time, level, and so on to scope with some other deviations or IQ mismatch compensation, which optimize also the things on this level. Some words to payload and to the first setting and preamble. Preamble is according to the standard. So if you are doing measurements on a Wi-Fi component which generates signals, or a modulator itself. So it's necessary to do this with a preamble setting. But if you are doing measurements on a device under test, an amplifier, for example, then you can do this with a payload, because here it's important to measure the deviations and the quality of the device under test with the help of the payload setting. So you have seen how Wi-Fi signals can be analyzed, but I would like to give you also some recommendation according the characteristic of the signal and according the Crest Factor. So because sometimes we are in a discussion with customers which are comparing results between devices or measurements to each other. And one additional fact, or one important fact, must be considered if we are talking about measurements and the comparison. It's the Crest Factor. So digital signals, modulated signals, have a Crest Factor in a different way. So for example, you have an averaged power level, but you have also to consider a peak power level, which depends on the modulation scheme, on the content of the signal, and so on. And to achieve the best EVM measurement results on the analyzer side, you must take care on the perfect leveling of the signal. For that, I have prepared a slide which gives you a better impression what I'm talking about. So on one hand, we have signals with a different Crest Factor characteristic. So in the middle, we have here a signal with a low Crest Factor. This means the difference between the average power and the peak power is not so high. But here, in this case, we did a wrong leveling. So that means we have here still a headroom for increasing the reference level and to use the complete range of the analog digital converter. So here on the right side, we did the things correct. That means we have done a perfect leveling with a low Crest Factor. That means we'll have an averaged IBM measurement result, which is a good range, compared to this here, where we lose performance of the analyzer. Here in this case, the EVM measurement result would be too low. On the other hand, we have also here signals which a high peak power, which means a high Crest Factor. That would also result in a low EVM measurement result in average, because so we have to take care on the peak power to avoid any overload of the stages and to have also enough headroom above the noise floor of the spectralizer and of the converter. And for that, of course, if this example shows that with the same signal power but different Crest Factors, the EVM result can be very different. So that's therefore my recommendation. If you compare measurement results, you have to take care also on the Crest Factor. Otherwise, the RMS values or EVM measurement results cannot be compared. So far the theory about Crest Factor, and let us go back to the measurement devices to show you this topic in practice. If you are talking Crest Factor, we have some possibilities on the signal generator side to have an impact on that for optimizing the Crest Factor, and which gives us then the possibility also later on for an optimized leveling on the analyzer side to take care more on the averaged EVM value with a lower Crest Factor. We have to go back to the block diagram of the signal generator, and then I go to the baseband part of the signal generator, and here we have implemented a setup for filtering or for a clipping setup. That means I go here to this part of clipping, and I told you that Crest Factor means the ratio more or less was the difference between the average signal level and the peak level. And here with the clipping setting, there are several possibilities, but one very easy possibility or to set up is clipping of the preamble signal parts to the level of the data part of the signal. Here it can be done with this simple switch, and in some cases it depends on the signal itself. So sometimes it has a huge impact or sometimes lesser impact. But here the SMW gives you an indication about this. Here on top, here we show the Crest Factor or the difference between averaged and peak power. And here, just by switching on the clipping, you can see a reduction of the crest factor, which gives us the possibility now to use the dynamic range on the analyzer side in a better way. In my practical demonstrations, we were dealing with a very simple signal on the physical layer. So it was a downlink signal for just one user. But with Wi-Fi 7, also some more complicated mechanisms are defined. You've heard it at the beginning. So we can combine something, we can generate several streams and so on, which extends the facilities of Wi-Fi 7. And for that, of course, so Jörg will give you some additional details about the very fancy extensions and possibilities of Wi-Fi 7. Jörg, please.
Yeah, thank you very much, Werner. I'm not sure whether they are fancy. Let's have a look on this. But of course, I mean, we are talking about extreme high throughput. And what we were focusing so far was on the physical layer, which is essentially the MIMO schemes. It is about higher bandwidth. It's a higher modulation schemes. But if you look on the reality, you have to have in mind higher MIMO schemes is nice, as I mentioned, on a mobile device or on small devices. The capability to integrate more and more antennas are quite limited. Having higher bandwidth, we talked also about, is not always possible. Not in all environments you can really use 320 megahertz. And also 4096 QAM is a very exciting technology, and we saw the test instruments which are able to handle this, and we have of course also Wi-Fi access points and devices enabling handle this hard RF requirements. But in the real life, you need also a kind of very clean RF environments, probably to be very close to the access point to really use these high modulation schemes. But we as user, we don't care about this. We would like to have more throughput, in this case, extreme high throughput. Therefore, they are looking also on other means how to improve the extreme high throughput. And this goes more on the MAC layer. And I would shortly like to talk about this because I think that's very, very important for the industry and very important feature. I would like to start with something that we know already for years, which is the multi-band access points. That means you find access points which are saying they are triple band, double band, quad band, and so on and so far. What are these access points doing? Yeah, they have essentially several access points on board, virtually and also physically. For example, one part operating in 2.4 gigahertz, another in 5 and 6, sometimes on the same antennas, sometimes they have using also different antennas. So the access points are already prepared to operate all these bands in parallel. But on the device side, this is still single connections, one connections on one band on one channel. So that means it's just optimizing the whole network, the access points. What they are doing now is to extend this kind of principle and say we would like to have now multi-link operation, which includes also simultaneous multi-link operation. That means in this example here, for example, this device can use, for example, here 2 channels, one in 2.4 gigahertz and one on a 5 gigahertz band, or also more channels, or also several channels in the same band. That's not defined. For what you can do in this, there are different applications. You can use this, for example, for so-called band steering. So you can have several connections in several bands, and you can always use the bands which is actually free. So this is, or has better RF conditions, let's say in this way, which of course improves the latency. You can also make a kind of load balancing using both channels in parallel if you have just 2 or 3 or however. You can also make some traffic aggregation. That means you can really use the full pipes, 2 or more pipes, to improve the throughput. Here we are coming to this extreme throughput. And you can also use this, for example, for traffic duplication, for redundancy, to make the connection more resilient, to improve the reliability, for example, for very important applications like in the industrial environment and something like this. So that's more or less the idea. So that means you would like to use different several channels in parallel. Looking a little bit on the details, how this looks like, for this you have still the normal physical layer, like you see here in this example with 3 links. You have a low layer MAC, which is related to the physical layer, and you have a kind of common MAC for all these multi-layers. The devices which are supporting this are called Multilink devices, like here, Access Pine Multilink device or Station Multilink device. And there are certain principles how you can use this. There's also the question, can you use for this multiple link or transmit only if you have a free link on all 3 links? Or is this independent? So there's several operations mode. But one mode is very important, also for the RF design. This is simultaneous transmit and receive. That means you can really have to one device and receive and send at the same time, which of course has some impact here, for example, on in-device interference and something like this. And with this, you can largely improve your latency and the throughput and so on and so far. For this, so I think that's a very important feature. It's as a top priority in a standardization and also on the Wi-Fi Alliance. So, and everyone is looking really on this feature to improve the throughput, because it is in this sense very interesting. You don't need more antennas. You don't need to go to 220 megahertz. You don't need to go to wider channels or to higher modulation schemes, but you can provide more bandwidth or more throughput with this. In other technologies, we know this as channel bounding or as carrier aggregation or something like this. So this is coming now to Wi-Fi. With this, I would like to close the part of Wi-Fi 7. There are a couple of more features, especially on the MAC layer. And I have to say, the industry is already looking on Wi-Fi 8, by the way. I think the standardization will start soon. Finally, I would like to give you a quick overview of the instruments and the Wi-Fi SASH solutions that we have already for Wi-Fi 7. What we saw and what Werner demonstrated today was our signal analyzer and also our signal generator. Here in this picture, for example, also the SSM. You can also use the VSE software. We have, of course, for the RF device designs related VNAs. We have a nice product which we showed also in the webinar before, the CMP 180, which is also supporting Wi-Fi 7 in a sense that it is able to go to address the whole spectrum and also the whole bandwidth and so on. We have, of course, OTR devices. We have everything for digital design, and we are also able to provide conformance test solutions for Wi-Fi 6, Wi-Fi 6E, and in the future for Wi-Fi 7. Finally, I would like to give you some recommendations for further reading. We have a nice white paper about the technology, so all the things that you saw today is described here in detail. We have also a short application note, especially to this, what we saw in these demos, with the generator analyzer for the typical things. We have an older webinar about Wi-Fi 6, Wi-Fi 7 with the CMP 180, and all the friends which are always struggling with all the letters in Wi-Fi, and I'm one of them. You can have a look on this, our famous poster about the history and future of Wi-Fi, where it is simply explained and you can put it on your wall. And with this, I would like to thank you very much. If you would like to have more information, just visit our webpage. And with this, I would like to close the session for today and thank also Werner for his contribution.
Thank you also, Jörg. And thank you for your time and interest on this webinar. Thank you.
네, 지금까지 저희가 준비한 동영상으로 와이파이 6에서부터 와이파이 7 그리고 현재 가능한 물리계층에 대한 시험 솔루션까지 내용들을 함께 보셨습니다. 예, 생각보다 조금 길었어요. 그래서 지금 시간이 3시가 살짝 넘어갔습니다. 그래서 오늘 진행된 내용 굉장히 관심도 많이 가져주신 것 같고요. 굉장히 많은 내용들을 말씀드렸던 것 같습니다. 시간 관계상 저희가 길게 말씀드리기는 좀 어려울 것 같고요. 오늘 뭐 초점만 말씀드리면 그 와이파이 7 같은 경우에 와이파이 6 대비해서 스루풋을 올리기 위해서 효율성과 이 플렉서빌리티, 유연성에 대해서 굉장히 초점을 맞춰서 개량이 되고 있는 것 같다. 뭐 이런 정도로 한번 말씀을 드려볼 수 있을 것 같고요. 네, 오늘 간단하게 시간 관계상 다 질문 굉장히 많이 올려주셨는데요. 이걸 다 저희가 답변 드리기는 쉽지는 않을 것 같고요. 우선 저희 이웅비 매니저, 기술지원팀에서 근무하는 이웅비 매니저를 통해서 오늘 간단하게 서머리와 이 Q&A 질문에 대해서 저희가 답변 드릴 수 있는 부분 한 시간 관계상 많이는 못할 것 같습니다. 이런 부분들 함께 말씀을 드리도록 하겠습니다.
네, 그래서 오늘 서머리 할 수 있는 내용을 몇몇 분들이 질문에 맞춰서 좀 보내주신 게 있으세요. 그래서 몇 가지 질문에 대해서 좀 답변을 드리면 Wi-Fi 6, 6E와 Wi-Fi 7 차이가 뭔지 궁금합니다 라고 하셨는데요. 금일 이 비디오에서도 많이 거론이 된 것 같이 Wi-Fi 6와 6E는 사실상은 동일한 스탠다드를 쓰고 있습니다. 802.11AX라는 스탠다드를 사용을 하고 있고, 기존의 Wi-Fi 6 같은 경우는 두 밴드의 대역을 썼습니다. 2.4GHz와 5.5GHz, 5GHz의 밴드를 썼는데, 점차적으로 이 디바이스들이 늘어나면서 주파수에 대한 과밀 현상이 발생을 했고, 그래서 FCC 쪽에서는 5.975GHz에서 7.125GHz까지 사용할 수 있는 주파수의 확장성을 주었습니다. 그 확장성을 주는 데 있어서 11AX가 사용된 게 6E라고 얘기를 드릴 수가 있고, 그리고 Wi-Fi 6와 Wi-Fi 7의 차이 같은 경우는 방금 전에도 최주영 매니저가 얘기를 했듯이 가장 큰 차이점은 높은 데이터의 처리량이라고 얘기를 드릴 수가 있어요. 그래서 오늘 비디오에서도 얘기했던 것 같이 기존의 Wi-Fi 6 같은 경우 1024컴을 사용을 했다고 하면은 Wi-Fi 7 같은 경우는 4096컴을 사용을 하게 되고, 데이터의 이 채널 대역폭 같은 경우도 기존의 160MHz에서 320MHz로 늘어나면서 데이터의 처리량 자체가 빨라졌다라고 얘기를 드릴 수가 있을 것 같아요. 그리고 또 하나로 또 이제 차이점을 얘기를 드리면, 이 플렉서블 관점으로 봤을 때 Preamble Puncturing이라는 기능이 적용이 되면서 좀 더 유저가 사용하는 데 있어서 플렉서블하게 사용할 수 있다라는 장점을 가지고 있다고 얘기를 드릴 수가 있을 것 같습니다. 그리고 다음으로의 질문을 보면은 질문들이 많은데요. 네, 그 Wi-Fi 7을 지원하는 RNS 테스트 솔루션은 어떤 게 있는지 궁금합니다 라는 질문을 주셨습니다. 비디오의 마지막 쪽에도 좀 나와 있듯이 금일 오늘 보여드렸던 장비들의 SMW200A와 FSW라는 장비가 Wi-Fi 7에 대한 지원할 수 있는 장비라고 얘기를 드릴 수가 있고, 이 신호 발생기와 신호 분석기 측면으로 보았을 때는 그 SMW와 FSW 제외하고도 SMM100A나 아니면 SMCV100B, 그리고 신호 분석기 측면에서는 FSV, FSVA3K, 그리고 VSE라는 소프트웨어가 될 수가 있습니다. 하지만 이 신호의 퀄리티 측면도 중요하지만 설계하는 데 있어서 이 컴포넌트를 이제 측정하는 장비인 네트워크 아날라이저 같은 거를 이용해서도 실질적으로 Wi-Fi 7을 개발하는 데 사용이 될 수가 있고, 그 이외에도 TX와 RX가 동시에 존재하는 CMP180, 그리고 컴포넌트 테스트를 할 수 있는 TS8997과 같은 시스템이 솔루션이 될 수가 있습니다. 네.
예, 오늘 다시 한번 저희 먼저 죄송하다는 말씀 드려야 될 부분이, 오늘 시간 관계상 지금 많은 질문을 주셨음에도 불구하고 저희가 답변 드릴 수 있는 부분 현장에서는 지금 여기까지가 아마 시간적으로 한계가 될 것 같아요. 그래서 이런 부분들은 이제 저희가 먼저 죄송하다고 말씀을 드려야 될 것 같고요. 오늘 질문 주신 내용들은 저희가 전부 다 따로 개별적으로 회신을 드릴 겁니다. 그래서 이 부분은 저희가 답변을 반드시 드리도록 하고요. 또 이렇게 앞쪽에서 그 시작하기 전에 이제 먼저 글을 올려주신 분이 계시더라고요. 그 자료를 어디서 다운받아야 되느냐고 질문을 주신 분이 계셨는데요. 저희 오늘 준비한 요 웨비나 내용하고요, 이 자료에 대한 부분들은 그 아까 비디오에도 마지막 부분에 그 백서에 대한 이야기도 나왔는데요. 요 내용들을 저희가 그 다시 보기 페이지에서 한꺼번에 같이 그 제공해 드릴 수 있도록 준비를 할 예정입니다. 그래서 오늘 참석하신 분들께는 따로 저희가 그 참석에 감사드린다는 메일을 보내드릴 때 해당되는 페이지에 링크를 함께 제공을 해드릴 예정이니까요. 그 부분 참조해서 여러분들께서 다시 보기 및 자료를 사용을 해주시면 될 것 같습니다. 예, 오늘 벌써 원래 저희가 한 3시 정도에는 정리를 하려고 생각했던 부분이 이제 생각보다 길어져서 지금 벌써 3시 8분이 됐네요. 오늘 굉장히 많은 분들께서 관심을 가져주신 부분이 이 내용이 와이파이 7에 대한 여러분들의 뜨거운 관심들을 표현해 주시는 그런 부분인 것 같습니다. 뭐 비록 아직 스펙이 완료가 되어 있지는 않기 때문에 조금 더 기다려야 되는 부분이 있겠습니다만은 와이파이 7의 그 추후 상용화 시점에서 또 저희들은 또 그에 맞는 내용들로 여러분께 또 준비해서 다시 또 찾아뵐 수 있지 않을까 이렇게 생각을 합니다. 오늘 다시 한번 그 시간 관계상 모든 질문에 대해서 현장에서 답변을 드리지 못한 부분 다시 한번 양해 말씀을 부탁드리고요. 오늘 저희 준비한 내용은 이 정도로 정리를 하겠습니다. 다음번에 또 다시 한번 재미있는 흥미로운 주제를 가지고 웨비나로 여러분들을 찾아뵙겠습니다. 오늘 참석해 주신 여러분들께 다시 한번 감사 인사드립니다. 안녕히 계십시오.